Okay, so uh, this talk, I'm gonna talk about discrete dynamical systems, a little distinct of the subjects that were being talked before me. We are going to talk about a specific kind of discrete dynamical system that has been called fat solenoidal attractors. This is mainly a joint work with Carlos Bocker, who introduced me, and with Armando Castro of Universidade Federal da Bahia. So the classical fat solenoidal attractors are due to Tsuji, our work, I think, over 2002, 2003, and it's a very simple model of dynamical system. You have a T of the cylinder. In the first coordinate, it's an expansion by L greater or equal than 2. And in each vertical, a contraction lambda. Lambda is smaller than 1, but not really smaller. And we have some translation factor, f, given by a function f. And if we figure the picture, we have L overlaps the image. That's why it's called solenoidal attractors, because when we iterate, every time we have L strips that whose images will intersect. We will have an overlap. And this overlap in each vertical is given by a contraction by rate lambda and some translation in the vertical given by this function f. Well, the main feature that we are interested is the attractor defined by this function and the problems such as the measure of the attractor and the invariant measures supported on the attractors. And Tsuji proved a very interesting results that if the dynamic T satisfies a certain transversality condition, then it admits an absolutely continuous invariant probability that we call ACIP. It's very interesting, this phenomena, because absolutely continuous invariant probabilities are usually associated to expanding maps or non-uniformly expanding, and it's not often in systems that have contractions. And this is the interest of this theory. The transversality condition, we will state in some slides, says that in some sense the expanding or unstable directions in some sense it spreads a lot. So it will spread over all the manifold. And if the attractor supports an absolutely continuous invariant probability, absolutely continuous with respect to Lebesgue, in particular, then it will have a positive area. So this is why it's called fat attractors, because it has positive area and satisfies the absolutely continuous invariant probability. And more, Tsuji also proved that this phenomena, this condition of transversality is generic in the sense that we can perturb every f of class CR from the circle S1 to the real line R. We can perturb in the CR topology that exists in F tilde arbitrarily close such that the corresponding dynamics satisfies the transversality condition. So this phenomena is generic among those kind of dynamics. Okay, it's really technical, this transversality condition. It's not quick to define, but I would like to try to show here the definition that Tsuji gave in his paper. We can consider the partition of the circle into the sets I minus 1 over L, I over L. And this forms a Markov partition. And for every word of length Q, we denote the rectangle RA defined by the iterates from times 0 up to K minus 1. That is, the first iterate is in the interval IAQ. The zeroth iterate, the first iterate will be in the interval a q minus 1, etc., until the iterate q minus 1. It's a rectangle, very easy to see, of length 1 over L, L to Q. So it's the rectangles with some dynamical sense. Well, if we iterate the rectangle RA and the time is 0, an horizontal line by TQ, the image we have is the graph of a function that we will denote as XA. This function is very important because the attractor is formed by these graphs. So the geometry of the attractor is the limit of these lines for words A of infinite length. The words A of Q length are good approximations. Well, we say that two words A and B are transversal at some rectangle, at some word C, if the derivative dsxa minus ds YB is greater or equal than 3 alpha 0 theta 2 Q for every points X, Y in the rectangle RC. So the tangent line is transversal of these graphs, and we have a measure where these constants are given by the dynamics. Alpha 0 is the CR norm of F divided by Y1 minus lambda, and theta is lambda divided by L. Oh, and this is the transversality between two words. We define a way of counting the transversality at time Q, tau Q, as the maximum for every words A and rectangle C of the words B that are not transversal. Sorry, I should have written A is not transversal to B at C. Okay, so it's the maximum number of non-transversality. And what we call the transversality condition is if tau Q is smaller than lambda L to Q for some Q. Okay, so this is the transversality condition. It's like not too much tangencies. And Tsuji gave you two examples. One that satisfies the transversality condition, a simple expansion by 2, contraction by lambda, close to a half, and the function sin 2 pi x. It has a very good graph with transversality between the overlaps. And this kind of graph, this kind of dynamics, the attractor will be the graph of a function. So we admit no absolutely continuous invariant probability. Well, this is just to motivate the previous work, and it was only known for dimension 2. So joint with Carlos Bocker, we decided to extend this kind of ideas to greater dimensions, considering dynamics T of the torus TU times RD, given by a linear expanding endomorphism in the first coordinate, given by a matrix E, a linear contraction CY, plus some translation F. And we have the similar ideas. Well, we suppose that T expands volume. actually we need a little stronger condition. Expanding volume would be the Jacobian of t greater than 1. But we ask this condition between the determinants and the norm of the inverse of this contraction. In particular, T expands volume. In particular, the determinant of dt will be greater than 1. And we remark that if T is conformal, then we have exactly the condition expanding volume. And well, in that work, the main difficult was to formulate a similar transversality condition. Now we have graphs of u-dimensional functions. So we consider the smallest singular value. Actually, for a linear transformation A of Ru to Rd, we consider the smallest singular value as a way of seeing how the graph is transversal to the domain, to the axis of the first coordinates. This is the smallest non-trivial zero singular value, because if the dimensions are distinct, we will always have some singular values null, but this is the first non-trivial. Okay, and we consider it as a way of measuring measuring the transversality. In this case, between the graphs of Sxy and Syb, that will be functions from the torus to Rd. And we say that these words are transversal if the smallest singular value of this difference is greater or equal than 3 alpha 0 theta 2q. Okay, for every xy in Rc. Here I didn't give so many details about the rectangles. We have a partition, a very smart dynamical partition related to the expanding map on the torus. Okay, so the constants are similar to before, the analogs now considering matrix. And joint with Carlos Walker, we proved that if T satisfies the transversality condition, which is exactly the same now, we define tau q and ask it to be smaller than the Jacobian to q for some q, then the dynamics admits an absolutely continuous invariant probability. And we also give sufficient condition for this transversality condition being generic. We had to give it a new condition if the contraction C satisfies this technical inequality. It's not so often, but it happens many times. Then we can perturb the function f to get some f tilde CR arbitrarily close, such that the perturbated dynamic satisfies the transversality condition. So this is a fat solenoidal attractors in higher dimensions. Okay, I think I will be quick here in the idea behind the proof of the genericity of the transversality condition, because in dimension 2, Suji, he had, when iterate q times L to Q pre-images. So we have L to Q cones we can see as unstable cones of this width, alpha 0 lambda divided by L to Q. And to be transversal, we want that these cones will be disjoint, and all of them contained in the same cone of width alpha 0. So this is reasonable to expect, because we have L to Q cones, but they occupy a very small length. Each one occupies lambda divided by L to Q. So for very large values of Q, the space that of these cones occupies is really small. So we can make the perturbation. That I'm not giving all the details, are very technical. Actually, we make a kind of probabilistic argument. We define a family of perturbations and prove that the probability of not satisfying the transversality condition will be close to zero. Okay. So, in higher dimensions, in the work with Carlos Bocker, the problem is that now the structure of these cones are more complicated, and the transversality is measured by the smallest singular value. So for each matrix, we consider this set that is a neighborhood of length R, Vy, but is not, it's a neighbor, but very big in some sense, because it's not contained in a ball. Of all the matrix, whole singular value of this difference is smaller or equal than R. But as I said, X can be very far from AI, and the smallest singular value be close. We want that these neighborhoods be joint for R equals to the theta Q and contained in the same cone with width alpha 0. So we needed to measure this volume, the volume of this neighborhood. As I said, it's a big neighborhood, but with a small volume. UD dimensional volume, the space of linear transformation from RU to RD. And we proved that it's bounded from above by a constant times R to U minus D plus 1. This is the, you can see more or less as a cylinder locally. So all these neighbors will together will occupy a volume. As I said, we have the degree of the expanding map to Q pre-images, and this will be the volume given by the lemma. If you write as some number elevated to Q, this is the number that we ask it to be smaller than 1. The condition, sufficient condition for making the perturbations. Okay, so this kind of result gave absolutely continuous invariant probability. The proof actually relies in a inequality, very often in ergodic theory, called Lassota-York inequality, involving norms L2 and L1. And people who are familiar with this kind of inequality know that normally Lassota-York inequality gives much more than the regularity of the invariant probability, give a spectral gap of the transfer operator, exponential decay of correlations, and much more things. But one hypothesis to have the spectral gap must be the compactness, or the space of the stronger norm must be compactly embedded, and this is not the case. So we are now continuing trying to make another analysis in order to get the decay of correlations, and inspired in a work also made by Tsuji, joint with Arthur Avila and Guezel, for dimension 2, that in the very same fat solenoid attractors, if this condition is satisfied, lambda to 1 plus 2s times L is greater than 1, and the T satisfied the transversality condition, they proved that the density of the absolutely continuous invariant probability is Sobolev regular. Is in the Sobolev space age S for this S of the condition. And it's interesting that if you have S greater than 1, then by Sobolev embedded steering, the function in AGS of the surface will be continuous almost everywhere. and we will have that the attractor has no empty interior. The density will be a continuous function, which is a topological conclusion unexpected. Okay, this work of Avila, Guezel, Tsuji, they prove Elassota, York, and they have a compactness of the a norm, which is the combination of a kind of anisotropic norm and Sobolev norm in another Sobolev. They prove that a certain Banach space embeds compactly in another one with relation of these norms. This norm is often in hyperbolic dynamical systems that it is equivalent to Lebesgue in the direction of the unstable manifolds, but it acts as the dual of another one in the stable direction, because we have distinct behaviors. So the anisotropic norm is a mix. In one side, we see as a density, in the other side as an operator, and measures the norm. I will not define it here. It's technical. And so, joined with Carlos Bocker and Armando Castro, we are trying to get some conclusion of the regularity, Sobolev regularity. This is a joint unfinished work. I will state we hope to finish as soon as possible. We consider now a skew product that is a expanding map in the first coordinate x, an expansion of the torus, and a contraction in each vertical RD. And well, now we do not have F because it's a skew product here of C. F can be seen in the very term of C. Sorry for writing it. And well, we'll prove that if we have this condition, notice that for C, S equals to 0, it's volume expansion, and we will have a little more than volume expansion for some positive S, and T satisfies the transversality condition, then the density of the absolutely continuous invariant probability is Sobolev regular, will be the Sobolev space HS of this U plus D dimensional space. And so we conclude not only the absolutely continuous property, but also the regularity of the density. And here we do not ask to be linear, neither the expansion, neither the contraction. And considering more spaces of norms with more regularity, we can conclude a spectral gap for the transfer operator. And we also need S to be greater than a half of U. It's possible to obtain spectral gap and exponential decay of correlations. And it's with the very same condition, but S greater than U divided by 2, and T satisfying the transversality condition, then there exists a Banach space containing CR-1 and contained in HS, such that the action of the transfer operator, it's an operator associated to these dynamics, in the space B has a spectral gap. And in ergodic theory, we know that if this operator has a spectral gap in a Banach space, then the dynamics has exponential decay of correlations. It's a system that mix exponentially fast. And joined with Armando Castro, we are trying to conclude even more, and we are trying to conclude and prove it, the differentiability of the density with respect to the dynamic. So we can consider this map that associates the pair phi C, which is the expansion and the contraction, which defines the dynamics that we are considering, to the density of the invariant absolutely continuous probability, which is in HS under these conditions. This map is differentiable. Actually, we can prove this regularity for large R. We have more than C1. It appears some technical terms here. We do not, but we are thinking are really big. So we can conclude a very good regularity of the density when we perturb the dynamics. And this is really interesting because all these three kinds of results that I have mentioned are usually associated to expanding systems, or non-uniformly expanding, piecewise expanding, but are not common when we have contraction. So these two features, the transversality condition and the expansion of volume, says that in a certain sense, these maps can behave ergodically as an expanding map. So I think I'll finish here. I thank you very much, all of you, for listening and following this talk. Thank you very much. Muito obrigado.